All right, welcome to the first real chapter of brand new information in AP Chemistry. This is the Electrochemistry unit. This is one of my favorite units in AP Chemistry. When I first took AP Chemistry, we did it in the traditional manner where we started with topics that we reviewed first from Honors Chem and then moved on to the new topics. Here we're starting with all the new topics first, and by the end of the year we'll actually get to the easier stuff, which we can easily review. Electrochem is really awesome, and I think it'll be really good for you to have this up front, and it'll be a pretty easy chapter to get through, I think. Today we'll be able to define and identify parts of a voltaic, or you may hear me refer to it as a galvanic cell. Both words are interchangeable in this case. We're going to identify oxidizing and reducing agents and balance redox reactions. So with the balancing redox reactions, you got a good chunk of that in your summer assignment. So I'm going to go fairly quickly through that today when we do the examples. But if you are really struggling with balancing redox reactions, I will have a separate optional play pause it for you with a couple of more examples that were not seen in the summer assignment, and that should be helpful for those that need it. We'll also calculate cell potentials for our voltaic cells. So we're going to review first, cover a lot of the electrochemistry vocabulary, and then we'll identify the parts of our cell, and then we'll have some practice problems identifying oxidizing and reducing agents and calculating cell potentials. Your homework, you'll see Quest Voltaic Cells Part 1, and that is due Tuesday the 26th at 11 p.m. And Voltaic Cells Part 2 is due Thursday the 28th at 11 p.m. There's a third one that you'll probably be A-OK to complete. That is called Standard Reduction Potentials. After this video, you should be okay to do that. But that one's not due until the following week, so I just want to give you what's due next week. Okay? So a review of oxidation numbers. These were the rules we talked about in the summer assignment. This should be a pretty straightforward concept. I'm not going to go over any examples for you today, but we know that neutral atoms have oxidation states of 0. Ions keep their charges. Oxygen is usually -2 unless it's in the peroxide ion form, then it is -1. Fluorine is always -1. Hydrogen is +1 unless it's a hydride, which we won't really see any hydrides anytime soon, but if it's a hydride, it's -1. And then we know the sum of the oxidation states is equal to the charge of our substance, or the charge of a polyatomic ion. If it is a compound, then the sum is equal to 0. We also have our rules for both balancing an acid and basic solution. I want to make sure you remember to write half reactions anytime we solve an electrochemistry problem, because with those half reactions, you're going to need one with oxidation and one for reduction. We're going to balance all the elements except hydrogen and oxygen first. Then we'll balance all oxygens with water, and then we'll balance all of the H's that we've added from the water molecules with H+. Since we add H+, that adds charge, so we need to balance that charge with the electrons that we are transferring. So then, after that, we'll multiply the reactions such that they'll be able to cancel out the electrons. And then we add our half reactions. When we add our half reactions, make sure to cancel out any waters and H+'s that may be able to cancel. If it's basic, it's the same steps 1 through 7, but then we use hydroxide to cancel out our H's. That's step 8. And then whenever we add OH to H+, we can get more water. So as a result of having more water, we may have to cancel out that extra water. Okay, here are the terms to know. I'm going to go through these fairly quickly, but I highly suggest pausing at some point to write these down. We have electrochemistry. What is electrochemistry? Electrochemistry is the study of the interchange of chemical and electrical energy. What that really means is we're studying the flow of electrons. So electrons are moving during our reactions, and we're trying to figure out how many moles of electrons, and where they're going. We have oxidation and reduction. With oxidation, it is the loss of electrons, which results in an increase in charge. With reduction, we have the gain in electrons, which is a reduction of charge. There are two ways that we can memorize these things, two little sayings that we have. We have Leo the lion says grr, which stands for loss of electron is oxidation, gain of electrons is reduction. Or the one that I always used, oil rig. Oxidation is loss, reduction is gain. Kept it simple. I didn't like Leo the lion says grr just because there's just more to say. I liked oil rig, so it's short and simple. There are a slew of mnemonic devices for this unit, so please utilize those. It'll make it very easy to remember where everything goes. Oxidation numbers we just talked about, that's the assigned charge on an atom. And then my favorite, oxidizing agent versus reducing agent. These terms are tricky. They're not very intuitive. They're often switched and confused. And when we look at the definition, the words in the definition are opposite that of what they are called. I know, it's weird. An oxidizing agent is the species that is reduced because it causes oxidation. It causes the loss of electrons. The reducing agent is the species that is oxidized and thus causes reduction. So we got to think about what those processes are. Reduction is gain, right? So if reduction is gaining electrons, the oxidizing agent is taking those electrons from someone else. When they take the electrons from someone else, that other thing is oxidized. It loses its electrons, right? It's a interesting dichotomy that we have to keep straight. We're going to look at a couple examples today, and we should be able to identify those with ease. But it is tricky, so make sure you get those ones straight. Okay, electrochemistry involves two main types of processes. With this play posit, we're going to look at galvanic cells, sometimes referred to as Voltaic cells. These specifically are spontaneous chemical reactions. One of the examples we have here is a battery. Towards the end of this unit, we're going to look at electrolytic cells. Electrolytic cells are not spontaneous, and they require an external electron source, such as a DC power source or another battery or something of that nature. But overall, both of these are considered electrochemical cells. Okay, parts of a voltaic/galvanic cell. So this is an example of the setup that you would see for an electrochemical cell. We're going to look at a lot of pictures very similar to this throughout this whole unit. And you even have to be able to draw some of these for the AP test. So we're going to get really good at identifying these parts and the way that they work. So the first thing is the anode. The anode is the electrode where oxidation occurs. The electrode, this is an example of the electrode. It sits in the water, not in the water, but in the solution, and it has a wire attached to it, and it connects it to another electrode in a separate beaker. After a period of time, the anode may become smaller as it falls into solution. We also have the cathode. The cathode is where reduction occurs. After a period of time, this may become larger due to ions from the solution plating onto it. So it may look bigger because the ions are becoming attracted. So the cathode may pull the ions out of solution, whereas the anode, the solution may pull ions from the anode. All right. You may also hear us refer to something as an inert electrode. An inert electrode is used when a gas is involved in our galvanic cell, or we have an ion-to-ion reduction. The common one we see is iron 3+ being reduced to iron 2+. So when we have something like that, we have the need for a platinum or graphite electrode. It is not actually part of the reaction, but it is known for being neutral, so it doesn't react, and so it allows the ions still to pass through. They are good conductors, but that's about it. They're not going to be part of the reaction, but we do need to recognize that those are valuable when we have ion-to-ion or a gas involved in our cell. We also have something called a salt bridge. The salt bridge is right here. Salt bridge, the purpose of this is essentially to complete the circuit for the cell. We are causing electrons to flow, and once they continue to flow in one direction, there's no way for them to get back. So we have a salt bridge in here. The salt bridge is made of a salt that salt ions rather. We've got in this example sodium nitrate. So the positive charges from the sodium and the negative charges from the nitrate migrate towards opposite ends, and this allows us to maintain chemical neutrality. So if we think about this, as electrons are flowing from one region to the other, then theoretically one side should become more positive and the other should become more negative. Well, this is true, it does, but only momentarily. The salt bridge acts as a way to balance those things out. As we get more electrons popping up in here, we have these positive ions that are coming down in here to balance them out. Same thing here, as it's becoming more positive in here, we have these negative ions coming down in to balance out the charge. So the electrons are still able to flow, but we have a nice little balance so that we can stay neutral. Speaking of electron flow, electron always flows from the anode to the cathode. If we were in a lab situation, the anode's not always on the left. You could be looking at it from the back side. It doesn't matter where it is as long as we're able to measure which way the electrons are flowing, but we need to know it does go from anode to cathode, and it goes through the wire. You also see up here we have a voltmeter. We'll talk more about voltmeters in a little bit. This measures your cell potential. Here I'm going to refer to it as EMF, which is the electromotive force, and it's usually measured in volts. Go into that in a little bit more shortly. Okay. So our mnemonic devices. So we have an OX. Oxidation occurs at the anode. They're all animal themed. We got an ox, red cat, fat cat. Red cat production occurs at the cathode. With fat cat, this describes the flow flows from the anode to the cathode. Another way you can remember is that the cathode is always positive. So the T is your plus sign, your positive sign. And then when we get to electrolytic cells, we've got EPA. In an electrolytic cell, there is a positive anode. And then another way that we can remember reducing agent versus oxidizing agent is OXRA and REDOA. I know, it's not the best one, but it works. OXRA, anytime I hear OXRA, I remember oxidation is the reducing agent. So REDOA is not as easy to remember, but OXRA sounds like a mystical beast or something. So hopefully that helps you there. Okay. Before you freak out at all this massive words on the page, there is a section here for those that really want to nerd out on voltmeters. Go ahead and you can pause and read over that fairly quickly. But the nitty-gritty of what I'm really caring about here is the first two definitions. We've got our cell potential and volts. So cell potential. There are three different ways we notate this. We have E cell, then we have the EMF, the electromotive force that I talked about, or we have epsilon cell. All three, you'll see all three when we're referring to electrochem. They're all the same number, it's just the cell potential. And the cell potential is just a measure of the electromotive force, aka the pull of the electrons as they travel from anode to cathode. And we measure this in volts, as we said earlier, through our voltmeter, but we need to know the unit of a volt. It'll be very useful when we get into the Nernst equation. 1 joule of work per coulomb of charge transferred is equal to 1 volt. So again, the bottom section, if you want to read more about voltmeters, because they are actually really, really interesting. One thing I do want to point out is that we need to be aware that a voltmeter is not always accurate. Actually, it reads a little bit lower than normal due to heat being lost, or energy being lost as heat through resistance in the wire. So we don't always think of that, but as a result, the voltmeter does read a little bit lower than normal, and you can read about how we could fix that if you wanted a more accurate reading. Okay. So here's another picture of a couple of different cells. Actually, it's the same cell. We've got zinc and copper. We also have something called line notation. So the line notation setup is the anode metal, and then a slash followed by the anode ion, followed by a double slash. And we've got a cathode ion and then the cathode metal. So I know here it looks like a slash. It's actually more of like a up and down, a straight line. So if we had our anode metal, we've got zinc, and then we've got our line, and then we've got zinc 2+, and then the double line. The double line represents the separation from the salt bridge, separation of the two cells. And you have 2+ and your metal. So if you were to look at a cell, you could decode it just like that, or they may give you a cell, or may give you the line notation, and you'll have to use that to figure out the half reactions necessary. One way you can look at it is an ion sandwich. The ions are always in the center, and the metals are the bread slices, and the ions are your filling. Okay. I know on the quest, a couple of your questions with the line notation will pop up, and it will ask you to go from line notation to half reaction, and then also from half reaction to line notation. All right, standard reduction potentials. So I mentioned these earlier. Each half reaction has its own cell potential. So when we look at half reactions, we actually have a nice little table here. You should have gotten this table in the formula sheet packet. These are all the different half reactions, the main ones that we'll be dealing with. Back in the day, they actually gave this to you on the AP exam, but they no longer do it because in the event that you need a cell potential, they will just give it to you. For the ones that you need, they don't feel like wasting your time anymore going back and looking through a table. But for the purpose of what we're doing in class, it's really easy to have a table ready. I've actually got two tables. There's this one, and there's one that's kind of like this. It's got a lot of the same information. Looks like the one in the Namesy packet, if you checked out the Namesy materials. So you see we have a half reaction, and we have the E naught, which is your cell potential. Okay. So each half reaction has one. The way we get those numbers is by measuring the potential against a standard. The standard is called the Standard Hydrogen Electrode. It's abbreviated as SHE or SHE. The SHE is assigned a value of 0 volts. So 0 is our standard. It's easy to tell in both a positive and negative direction the potential of the other half reactions. As I stated before, you may have an inert electrode. Whenever we measure with a hydrogen electrode, we're using platinum, and the platinum is actually bathed in hydrogen gas at 1 atmosphere. We also have standard conditions. So you saw before it said E naught, or the naught symbol. All that means is that we're using standard conditions. Standard conditions is 1 atmosphere when we're dealing with gases. It's 1.0 molar for solutions. And both gases and solutions are at 298 Kelvin or 25 degrees Celsius. So when we're talking about E naught, the E cell, the EMF, and the epsilon cell that we saw before all have this little naught symbol. It looks like a degree symbol, but it's not a degree symbol. It just means the standard conditions. That may look familiar. You may remember doing free energy with delta G and delta G naught last year in honors. It's the same thing. It's just the standard versus non-standard conditions. Okay. So when we're looking at these tables of reduction potentials, the elements that are the most positive up here, elements that are the most positive are easily reduced. So generally nonmetals, you see here, this one's actually F2. So fluorine can be reduced to fluorine ions. Elements that are the least positive are easily oxidized. So then down here is actually lithium. So lithium plus, and we got Li, solid, and then here we go from F2 to F minus, or 2F minus rather. So given that we know that the higher the number, the more easily reduced it is, and that the lower the number, the more easily oxidized it is, we can use this to tell the strength of our oxidizing and reducing agents. We can also treat this as an activity series. So metals that have less positive reduction potentials are more active and will replace metals with more positive potentials. Okay. This is the other table that you will see in your packet. This one is very useful. This is not an official one from College Board, but it will show up in your quests. And actually, one of the examples we do today will use one of the electron potential from this. Okay, this part's really important. We've got calculating standard cell potentials. So we need to be able to differentiate between the element being oxidized and the element being reduced. And we want to do this by using our table of reduction potentials. We need to remember that the ones that are more positive get reduced. So we also therefore need to remember that when we get reduced, that means our charge is decreasing. So if we're really positive, we're becoming less positive. If we are negative, we're becoming more negative. You want to write both equations, both half reactions, from the charge with their voltages as is. So we don't want to flip any signs to start. We want to just write down what we have, and we can worry about changing signs later. We can reverse the equation that will be oxidized and change the sign of the voltage. This way, we want to keep the thing being reduced in the normal order. The reason we flip the one being oxidized is because we want the thing being oxidized to have the ions in the appropriate place, right? These are standard reduction potentials in our table, so they're all describing the reduction process. We're going to have to reverse the equation being oxidized because it's the reversed order, right? We're then going to have to balance the two half reactions. Remember the part where you may have to multiply to get your electrons to cancel out? That is a great step. Go ahead and do that, but do not multiply your voltage values. Voltage values can be reversed, voltage values can be added together, but they don't multiply at all. So that's the big rule. Don't multiply your voltage values. Then you add your two half reactions together, and then you can also add your voltages together. And our equation for that is the E cell is equal to the E of oxidation and the E of reduction.